Okay. So thank you, Eve, for introducing me, and thank you for inviting me to talk to you today about solar thermal energy, which is like the less known cousin of the solar energy possibilities. And my name is Audrey, and I am a research engineer in the laboratory that you introduced. That is indeed processes, materials, and solar energy. And we work on a lot of fields regarding this, and specifically in thermal energy and concentrated solar thermal energy. And for my part, I work more on the material aspect, which is what I will focus on today. So I hope I don't have to convince you that, yeah, global warming is real and climate change is real. And we've heard about all the things that we can do as citizens in this area. So I won't be listing them. But what we can focus here today in the solar aspect of this question is working on here. Well, you have photovoltaics, you have solar thermal, so that's mostly for residential use. And of course, we will talk about how to produce green power with this. So this is one that you've seen before, but just to remind you about, yeah, the power of the sun, if we can call it that. Sorry, you don't see the titles here. That would be, yeah, better. Okay. So to remind you that, yeah, the sun is very, well, powerful. We have a lot of energy coming from the sun that is arriving. That is, well, of course, if we find a way to use it, it has a real great potential. And it is said that it represents about 1,400 times the energy that we consume as humans on Earth. So a lot of power there, of course. Hello. There. So just a few words. What is the difference between solar PV and solar thermal? In really simple terms, well, with solar PV, you will directly generate electricity. And with solar thermal, you will generate heat. So in other words, the definition, you can, no, I can't put it, okay. You can consider that solar thermal energy is the conversion of solar radiating energy into thermal energy, into heat. Okay, that's the basic definition. So starting from there, not responding very well, okay. The principle is that you have to channel this energy, the solar radiating energy, with what we will call a collector or an absorber or receiver, depending on the technology, which is made of one of several materials that we will talk about. And this thermal energy, well, you want to, to convert the solar radiating energy into thermal energy, into heat. So that's point 2. And point 3, which is also equally important, is that you want to transfer this energy to something. So usually it's a heat transfer fluid that will extract the energy that is the heat that is produced in the collector, the absorber. And so you can use it later on. So with this simple principle, you have many applications possible. We can arrange them by types of applications. The first type of application is that you can use directly the heated fluid. This is what you do when you produce, for instance, hot water for your house, for instance. And the second option is that you can convert this thermal energy into another form of energy, or several of the forms of energy. So for instance, this is what happens when you consider solar thermal electricity generation. You go from thermal to mechanical energy well, thermal to produce steam, then you can activate a turbine, a steam turbine, and then you can produce electricity like you would do in any other kind of power plant. Okay, so keeping this in mind, we will focus now on arranging and describing solar thermal from the view of the collectors. because it is the most critical component of this technology. And what does it have to do? A lot of things. It has first to harness solar energy, meaning that it has to absorb it efficiently. It needs to convert it into thermal energy, so it needs to heat up after absorbing it. And it needs to transfer it to the heat transfer fluid, so we need also to conduct heat. So based on this, the outline of the rest of the talk would be in three main parts. The first part, I will introduce the solar thermal technologies by collector type. So we will review quickly the principles and applications, it's written twice, of these solar thermal technologies, and we will focus then on the surfaces that are needed to these applications. And in the second part, we will talk about the surface functionalization for solar thermal. So we will talk about, not specifically in that order, but we will talk about the optical behavior, some basic definitions and the requirements for this energy. Also, we will talk about optical theory a little bit that is needed to predict and optimize the optical behavior of these materials. And we will also see some applications of these optical theory to solar thermal materials specifically. And in the third part of the talk, we will talk about a little bit about the question of the durability of these materials and their aging. So it will be put in regard to the working conditions that can be demanding, especially when you consider concentrated solar, and the consequences on the materials, and what you can do, well, to predict durability and to improve the durability of these materials. So looking at solar thermal technologies by collector type, well, you have different options here. So we will start with the most simple, the simplest of ones, which are the unglazed collectors. And it looks like this. And it's usually something that you use to heat a swimming pool. And so you have basically a pool here, you have a pump, and you have this solar tubing here. It's usually black plastic, and you run the water of the pool through the tubes. They are heated by the sun because the tubes are black, and they are put back in the pool. And so you can heat your pool by a few degrees. And I show you this because this represents actually a large capacity of solar thermal worldwide, because in the US, this is what they use the most for solar thermal, and in Australia too. Okay, a bit more complicated technology now. We can talk about what we will call the solar thermal panels, to differentiate them from PV panels. But they're, you can find them on roofs as well. So sometimes it looks like a PV panel. So these ones are usually used to produce domestic hot water, for instance. You put them on the roof, and it works something like this. It's connected to the water heater, the water tank, which is still equipped with a resistance with an electrical input for when you don't have sun and for the night, etc. So this collector will provide some heat water, and you have a pump here that will activate depending on the temperature difference between what is inside the collector and what is inside the heater. So if you have a temperature difference that is big, well, if you have a lot of heating from the roof, well, you can send it to the water heater. And if you don't have, well, if your water here is cold because you have used it, then you can also activate the pump to send it to the water heater. This is also something that you can use to heat floors. in domestic use. So we'll call it DHY for domestic hot water, W, sorry, and for heating. Okay. So let's focus on what types of solar thermal panels there are. There are two main types. There is the flat plate collectors, like this, and the evacuated tube collector, like this. So I will put a little focus on the two technologies. For the flat plate collectors, you have here the main part, which is the absorber, which is this black plate here, which is usually made of copper, because copper is a very good heat conductor. And you paint it with a black paint or a black coating that we'll talk about a bit later. Here to absorb. So this is the absorber plate. And below that, you put some thermal insulation. And above that, you put a glass with an anti-reflective coating, usually to improve the absorption and create a greenhouse effect. So it's very, very simple to understand. And for the evacuated tube collectors, you have two main technologies, which are the, we have these tubes like this that are inserted in a header. And you have two possibilities. One, you directly send your cold water inside and come in, well, is heated on the roof and comes out hot here. That is in the shape of a U, so it's the U type, the U pipe type. And you have also the heat pipe type. In that case, you have a copper heat pipe here, where you have another fluid that is trapped inside and that is heated by the sun, and the it's in liquid form, goes into vapor, and then the heat is extracted at the header here inside the system, and it goes back to liquid form, etc. So it's a cycle inside the heat pipe. And this is the technology that is most used. It's interesting because if you have one tube that is failing, you can just remove one without affecting the whole system. So if we consider materials and surfaces here, let's have a look at the absorber plate. So we have actually two options. One option is the absorber plate, where you have either the heat pipe or the tubing that we talked about just before for the flat plate, and you put this inserted in another plate that is black, and its role is to absorb solar radiation. So that's what usually a bit wavy to trap a bit more radiation, and it's black and sometimes with this blue aspect, because there is actually a complex coating on top of it, where you can have an anti-reflective effect on top of it. So that's why it resembles in this way solar PV. And another option is to, and that's for the evacuated tube collectors mostly, is that you insert the heat pipe inside a heat transfer fin, which is usually made of aluminum like this, or with different shapes like this. And the role of this fin is to to create a contact and a heat conduction between the heat pipe that you want to heat and the tube, the vacuum tube, where was added here in darker blue a layer that is an absorption layer. It's a coating. We'll talk about that coating a bit later in more detail, but it's a coating that has the ability to absorb radiation that is put on the surface of the inner tube. And you have a contact here between the absorption and the heat transfer fin to heat the heat pipe. So these are the two main options and coatings in both cases. So we have now said a few words about how to produce, let's say, hot water for domestic use mostly, we can consider that these types of collectors are without concentration. So why do we say that? Because there is also the option of concentrating the solar irradiance, and you have more technologies and more solar collectors here accessible. So without concentration, you have a temperature range that is like this, let's say around 100, 120 degrees. You are limited in the amount of heat you can produce. What we can say to finish on these two technologies here is that you can reach higher temperatures with evacuated tube collectors because you have a better insulation. You have less. Because you have a vacuum insulation. In fact, between two glass tube, sorry. So you can reach higher temperatures. You have a better efficiency, if you want, and less radiative losses. Okay, so going back to with concentration. So what is solar concentration? Well, we can consider that concentrating the solar radiation is equal to having several suns instead of one. So this is not exactly how we do it, but it's a good image of what's happening. It's like having a magnifying glass, if you want, that you put between the sun and the absorber or the receiver. So you have more power to send to the absorber and to the fluid. A few things to consider with solar concentration, however, is that for one, well, in the other solar technologies, you can use the global irradiance of the sun, meaning that you can use what is directly coming from the sun disk, what is coming from the sun corona, the circumsolar, and also what is diffused. So what falls on many objects on Earth and is diffused in many directions, different directions. But with concentrated solar, you need to be able to know where the sun rays come from where they come from, in order to send them in a specific direction, i.e. on a solar absorber. So in fact, you can only concentrate what is directly coming from the sun disk. So it means that for solar thermal without concentration, and for PV, you have this map of irradiance, which is the global irradiance. So you see, these famous sun belts with a lot of countries where you have a lot of solar resource. But if you consider only the direct irradiance, then, well, you see it's not exactly the same color scale, but you see that it is reduced. The regions are not the same. Well, actually, they are the same, but it's less large. Well, you can consider that everything that is from orange to pink is a viable option to consider solar concentration, and specifically if you want to install solar plants. So you still have here the western part of the US, you have South Africa, Australia, you have North Africa and the Middle East. And actually the highest that you can find is in Chile, because you have these salt deserts that are at high elevation. And so the atmosphere is very pure and you have a lot of sun. And so it's one of the best places to use solar concentration on Earth. So a definition that is interesting, well, it's simplified here, but you can consider that the number of suns that you can reach depends on the area, the surface of the collector. Well, usually it's a mirror and not a magnifying glass, but you get the idea. So this area compared to the area where the solar irradiance will be focused. So you can consider, we often talk about a focal point. Actually, it's more of the spot because, you know, optical errors and aiming errors. So it's not exactly a point, but it's kind of a spot, and it can be quite a large spot. So there's, yeah, a spot, yeah, big large spot. So the solar concentration ratio, or the number of sun, C, is basically the ratio between the area of the collecting part over the area of this focal point. This is a simplification for experts, but it gives a good idea. Okay, so if we look at the technologies, they're not really say technology with this slide here, but yeah, it's an image. So you can have an idea with the solar lighters, for instance. You have this parabola here, and if you put something that is flammable at the focal point, you can light it. You have the solar cookers. It's basically the same idea. You put mirrors around this pan that can be considered as the absorber, the black absorber, and the fluid, the heat transfer fluid, is the water that is inside. And you even can find and buy solar barbecues. I have one at home. It's quite fun to use. And you put a pan here or a grill at the focal point of this parabola here, and you can reach temperatures enough to cook things. Now, on a much larger scale, you have on the opposite side, actually, you have solar furnaces. And this is where my lab is installed, part of it anyway. So it's an 8-story building. It's an old building that was originally built for this specific purpose of creating this solar furnace in the, well, almost the 70s. So you have a big parabola of mirrors on the north side of the building. And if you look at how it works, well, we have a field of mirrors on the other side. I have a quick view of the photo here. A field of mirrors opposite this the building here. And the role of these mirrors is to catch, and to follow the sun throughout the day, and to send it, to reflect it towards the parabola. Okay, so they are called heliostats because they move like sunflowers, let's say, which is, I think, the Latin word of sunflower or something like heliostat. It's close. So you have the idea that it follows the sun throughout the day. And this is, of course, not moving. And then you have a second reflection on the parabola here towards the focal point here. That is on this inside this building here. Okay, so you have 2 stages of reflection. And there are what we call lower power solar furnaces on the other side of the building, also with 2 reflections as well. We have 3 heliostats here, with here on the 6th floor of the building. We have also some parabola I will show in a few seconds. So this we've already seen, and this is a view of the focal point. So you can see that it's quite wide because of the size of the system. We have something that is close to 1 meter wide for focal point, which is then more spot than a point. Now, these are what we call the medium-size solar furnaces with lower power but high concentration. High concentration. Why? Because the size of the focal point is much smaller, in that case, a few centimeters. So it's really powerful, and we can use this to reach high temperatures almost instantly on materials. So we have like I said, a first reflection here on the heliostat, and going up in the building to this parabola here, and then concentrating on the focal point that is here. And we have shutters to modulate the solar irradiance that is seen by the materials. So I think it's the next one. Yes, I have a short video on less than 2 minutes that explains it all.
How tight does this focus? Can we see it?
Just look, yes. By spraying some water.
Oh my God. So if my hand's here, it's okay, but if it went there, what would happen?
Not at the focus. Here it's okay, but...
And even a mirror this big, would it be powerful enough to kind of set light to something?
Yes.
Can I try it?
Go ahead.
Okay, show me the focus. I'm okay. Oh, life. Can we do that again? That's astonishing. I've never seen anything set light to wood that quickly. How hot is it in there? What temperature does it get to?
At that focal point, we can reach a temperature higher than 3,500 degrees C, and there is currently no known materials that could resist this.
There is nothing on Earth that can withstand the temperature right in the middle there.
Nothing.
And I'm pointing at it.
Exactly.
Just 2 square meters of sunshine can melt steel pretty easily. I would love to try and weld some stuff with sunshine. It'd be really nice. If you had 3 people sunbathing, they would be collecting that amount of sunshine. And look what it does. Despite having traveled 93 million miles, the energy of the sun can even melt rock. Look at that. See, to me, that's far more amazing than melting steel. Like, I see steel melt every other day, but I've never seen anything like that.
So this is what we do when we have visitors in our lab. It's always nice to do that. Well, that was just a picture in case the video wasn't working. And this is actually something that we do every time to really check the position of the focal point before putting our movable thing here to the focal point, so we don't, melt everything. Okay, so now let's switch to the different types of concentration. There are different types. This was just one type, the solar furnace, but it's a specific case. So you can find a very simple one, which is called the compound parabolic concentrator, or CPC. Well, you can reach the value of the few suns, 1 to up to 10 suns, depending on the size of it. And it's in this W shape here. So it receives the solar radiation from there and reflects it on a tube. So it's linear concentration. You focus in on a tube that you put in the middle. So it's often used in combination with evacuated tube collectors. So you use less tubes, or it's a larger system than before, because you need some space to put the W shape here. But you have eventually more efficiency, a higher efficiency of the system than the previous one. So you can reach higher temperatures. Another type of concentration is the parabolic trough. So it looks like this. You have a large mirror like this. Actually, it's a bit more open than this, a few meters wide here. And again, you focus, it's a linear concentration, and you focus the solar radiation on the tubes that are here. So you can reach higher concentrations, let's say in the range of 100 suns, even a bit more than that. And you also have what is called the Fresnel linear reflector. So why is it called like that? Because it's based on the Fresnel lens principle, a Fresnel lens, like you have on your car lights. It's the idea that with a lens with this shape here, you can have the same focal point as with the denser lens like this. And so you recreate optically, the same effect with less materials. So it's lighter, it's cheaper. So the idea is the same here, except we are recreating the same effect as the trough, but with less mirrors. So instead of having this large trough with a lot of materials, we have this almost flat mirrors here that you can put in different orientations. So you would create the concentration on the absorber tube, like in the trough, except it's less efficient. So that's why it's usually you have a secondary mirror that catches what has missed the absorber tube by not a lot. And so you catch it again and send it back also to the absorber tube. So you have a bit higher efficiency. It's still less efficient than the parabolic trough, but it's also cheaper and lighter. You can find this type of reflector in small systems as well. It's used like this one. So here you have a range of mirrors. You have two different sets, one range of mirror focusing on this sole absorber here and the same here. So you have two absorbers. And this is used in systems like this. It helps, it has a higher efficiency than flat plates and evacuated tube collectors, as you can see here. So this is the efficiency as a function of temperature. And so you can see that you can reach higher temperatures or have a good efficiency at higher temperatures anyway. And this can be used not only for heating, but also for cooling, for air conditioning applications. So going back to this again, now we have added these types of concentration, CBC and linear, the different linear ones that we have seen, where you can reach higher temperatures. Actually, you can reach up to a few hundred degrees. So in addition to domestic hot water heating and cooling that you had before, we have also other options. Now I'll put that here. And one option is process heat. So why am I talking about this? It's because, well, when you look at the world energy consumption by end use, you can see that basically half of the energy that we consume is to produce heat, is for heat. We need heat directly. And it is half of it for industrial processes and almost half of what's left to heat, well, space and water for buildings. Okay, so we need a lot of heat directly. And solar thermals is a good solution for that because it produces heat directly. You don't have to produce electricity and then transport it and then transform into heat. So that's why we have now a tendency to go to larger scale solar heating and cooling, like I said, with higher temperatures. So now we can find some applications in residential and commercial areas, larger areas. So we go from isolated buildings to up to whole districts that are where you produce heat and hot water up to whole districts like this. You have in the Netherlands, this is called, they called it the Sun Island, and this is solar thermal here. And you can put them in fields, on roofs, on walls even. So you can have larger capacity. And regarding industrial heat, it has been aptly named SHIP, solar heat for industrial processes. If you look at the temperature levels that are needed in the industry, in most industries, well, you have a lot of it, depending on the sector, you have a lot of it that is below 100 degrees or up to, let's say, 400 degrees, where solar thermal itself can provide a lot of that. And if you add the concentration part, well, you can reach easily these temperatures and even above these temperatures. So if you look at a distribution of the different collectors, solar thermal collectors, and the temperatures that they can reach. You can see that, yeah, this is what we have seen for lower temperatures. So it's mostly for domestic use. You have the flat plate collectors, the evacuated collectors. This is where it starts being interesting for industries, where you can reach higher than 100 degrees. And for that, well, you have the concentration, the linear concentration options that we've seen. So we have parabolic trough and Fresnel collectors. So you have small scale systems that can be used by industries. Sometimes they put it on roof even. And I haven't talked about this, but there are also advanced technologies of evacuated to collectors, and you have flat plate collectors that are also used under vacuum, so they're more efficient. So they can also be good competitors to concentrated solar for industrial processes. All right, and this is the last part about the solar collectors that we can add. It's when you want to, if you can reach higher temperatures, so with higher concentration, you can even consider having a solar thermal power plant and to produce electricity. So if we look at, well, how power plants usually work, you have, well, you need a turbine and an alternator to change mechanical energy into electrical energy. With some renewables, you can directly, let's extract mechanical energy, like with the hydraulic wind or tidal. You can also create it from thermal energy by combustion of fossil fuels or biomass, nuclear fission or geothermal, where you change the water into steam and then use that steam to activate the turbine, the steam turbine. And in the case of solar thermal, well, you will create this thermal energy with from the radiating energy of the sun by concentrating it to have a higher amount of heat. So you have two main steps. You have the conversion of solar light into heat, and then, well, a classical thermodynamic cycle. So a simple sketch of what it would look like, a solar thermal power plant. You have, here you find the turbine and the generator and the cooling water, as you can find in any power plant. So you have usually two separated cycles with two separated heat transfer fluids, not always, but in most cases. And that's why you have a heat exchanger here between the fluid that is heated inside the solar field, and that goes to the heat exchanger, to the turbine and generator, and then you cool again the fluid and you send it back to the solar field. And you usually have an additional heating in case there is no sun, so you have a power plant that can be used. In that case, it's a hybrid option. It's not always the case, but that's that can be useful. And if you don't have that, you can have storage as well. You can store the heat that is produced to be used when there is no sun. Okay, so what's of interest for specialists in surface engineering is the solar field. That's where a lot of things have to happen. So the solar field is a field of solar collectors put together where you harness the radiation from the sun and you transform it into thermal energy, and you have a heat transfer fluid that goes through that extracts that energy. A classical view of the types of concentration is a table like this, where you consider the receiver or the absorber, as we folded before. You have two types of concentration: linear concentration, like we've seen before with the parabolic trough and the Fresnel reflectors. So you concentrate the radiation on the line. And you have the point focusing option. So this is the case of a parabola, like the the second stage of our solar furnace from before, where you have a parabola here and you concentrate on a point here. And then you have the option of what is called the solar tower or central tower, where you have heliostats on the ground that follow the sun, and you have a fixed tower here with a receiver on top, where you send all the radiation there to heat up the receiver that is there. So that's why you have these two lines. In one option, the receiver is movable. In these two options, parabolic trough and parabolic, actually the mirror and the receiver move together. And you have a part where the receiver is fixed, which is the case for linear reflectors and central receivers. And that can be interesting because, well, as you understand, you have if we go back to the one before, here you have to send fluid inside the solar field and, well, in this way actually, and going back there. So you have a working fluid and you have a lot of connection and tubing to do that. So if you don't have to move the receiver, you don't have to move the connections for the tubing as well. So it's technologically speaking, it's easier if the receiver doesn't move. So that's just a view with pictures from there. So that's one that is in France, actually, I think this one, and this one too. And this is a view from the US. So you see here the trough with the line of tubes. Here the frontal mirrors. The receiver is up there, and you have a design view of a tower. There actually exist. I just didn't put a picture there, but they actually exist. There are quite a lot of them in the world. And so you have a field of heliostats here and the central tower with the receiver that is receiving solar light. That's why it's so bright like this. Okay, just a few words about how to consider these in regard to the temperature range. Well, that's the most important thing that we will discuss here. The temperature range that is reached. Well, for these linear technologies, you are around 500 to 600 degrees. This is actually, you can regulate this depending on the fluid that you want to use. So for parabolic trough, you use oil, synthetic or mineral oils, and molten salts also. So in that case, the temperature range is limited by that. So for oils, it's a bit lower, and for molten salts, it can reach this temperature. For linear Fresnel, usually, well, we found a lot of options where you produce steam directly. So it's called DSG, direct steam generation. The interest is that you only have one heat transfer fluid in the whole plant instead of two, and no heat exchange. And so you have less losses, less heat losses, because you don't have to exchange the heat. And the tower, you have the possibility, you have high concentrations, depending on how many mirrors you use. And you can reach higher temperatures there. And the idea is that, so for now, they are using steam and molten salts, mostly as heat transfer fluids. But the idea is that we could use an air turbine, a gas turbine, instead of a steam turbine, and reach higher temperatures. So it is possible. The power is there. Needs to be adapted to the to other systems. Okay, and going back again to the components and the surfaces that are of interest for us. If you look at the different technologies, so I've removed this one because it's not really used to produce electricity, or in very only small, well, some examples, but mostly you will find these three technologies. Historically, the parabolic trough is the more popular, and what is built now is more towers, and there are some Fresnel. There is some Fresnel as well. So you can, if you take a look at the three different types of receivers, here for the parabolic trough, you have a metallic tube that is painted in black, and it is protected by a glass tube, and you have vacuum between the two. So it's more efficient thermally, and it protects also the paint. Well, actually it's a coating that is on top of the metallic tube. So it works in vacuum. And with these two, the tube, the same type of tubing actually, here and here, if you could take a closer look, this is also tubing piping, painted in black. Well, in that case, it's in air. Here it's protected by a glass window, but it's not under vacuum. So it's, again, cheaper. The technology is cheaper because the problem is here, if you put it in vacuum, you have a different thermal expansion between the metal and the glass. So you need special bellows to account for that. And so it's more expensive. So here you don't have vacuum, just a protection behind glass. And here you have no protection at all because it's too hot, basically. So what we can retain here is that in all cases you have absorber tubes that are metallic tubes and that are covered by something. So if you look at the different types of surfaces that you can find in solar thermal and concentrated solar thermal, you have the concentrating mirrors where, well, their role is to reflect solar irradiance, so they need to have a high reflectance. You have a protective glass in some examples, like here and the Fresnel. So that one, well, has to transmit solar radiation as much as possible. And there is the thermal absorber, which needs to absorb this solar radiation, so it needs to have a high absorptance. So three types of surfaces and three types of materials that we will talk about later on. And just to say that, depending on the technology, you have a number of these surfaces, and sometimes you have several or not at all. For instance, in the parabolic trough, you have one of each, because there is only one reflection. For the linear Fresnel, you have a secondary mirror, so you have two mirror surfaces and one glass, protection glass. And what could we say? In the tower, you have the reflection, but you don't have any glass for transmission. So I'm saying that to show that there is also, there are optical losses that are inherent to using more than one of these surfaces as well. So if we consider from the point of view of the surfaces of these solar thermal components, actually these are rarely bulk components. You have more in most cases, you will find that you have a support material that is chosen for its characteristics, mostly its price, because this is the most matter that you will need. So you need it to be cheap, and it needs to be in the case of absorbers, for instance, resistant to high temperature, to high pressure. If it can be mechanically strong, it's a better choice because it's easier to handle, to install, and for its use as well. But usually this support material doesn't have the optical properties that we are looking for. So we just, have to functionalize their surface. It's enough by applying surface treatments, usually coatings, to give it this apparent property that we need and that this support bulk material doesn't possess. And in our case, specifically to reflect or to absorb or to transmit better sunlight. Okay, so surface treatment, like I said, they include thin film deposition. There's also some surface texturization in some examples, but mostly it's from coatings. And they're usually too expensive or too soft to be used as support materials, as we will see. So the good thing is that you only need a small amount of them if you use them in coatings. So in the case of solar thermal materials, we will focus, no pun intended, on the functionalization of their optical and thermal optical properties, because yeah, some of them are used at high temperature. So we need to understand what are their optical properties at high temperature. And I think the first part is over. So maybe I'll just say a few words about part 2, and then we can keep the rest for the second part of the talk. So now that I've introduced all of this, in the second part, we will focus on the optical behavior. Well, so it won't be a linear presentation, point 1, 2, 3. It will be all mixed. We will consider for the different applications and for the different components, the optical behavior that is needed. And we will define some of it as we go. And we'll introduce also some optical theory that we need for these specific applications. And then I will give you some examples of real materials that are used in solar thermal and concentrated solar thermal in regard to the support material and the coatings that are used as well. Okay, I think we could stop here and go back to the rest later. So as I was saying before, we are going to look into the different requirements that are needed for the different types of surfaces that we were discussing, the mirrors, the glass, and the absorbers. And we are going to look into some notions of optical behavior and optical theory to do that. Oops. Je suis sortie du... So a few words about the optical behavior, something that you probably already know, but it's always nice to have a reminder of this. When you have an interaction between an incident radiation, electromagnetic radiation at the surface of a material, well, that radiation can either be reflected at the surface, so it doesn't go inside the material, or it's transmitted, it goes through the material. And what is not reflected or transmitted is absorbed inside the material. So you have a conservation of energy like this, reflected plus absorbed plus transmitted equals 100%. C'est celui-là. Hello? Okay. Ah, did it again. J'appuie sur entrée. Si je fais ça, c'est pas partagé. Non, là, c'est pas partagé. Désolée. Il faut que je fasse avec les flèches. Ah oui, avec les flèches, ça ne va pas marcher. Et vous ne voulez pas prendre le... Ben non, parce que ça ne se voit pas dans l'enregistrement. Je montre un pointeur là-bas. Ah oui, non, on ne voit pas. C'est pour ça que je fais la souris. En plus, on ne tord pas le cou comme ça. Donc, pas entrer. Voilà. So something to remember about these values is that they are wavelength dependent, and they depend on the incident angle of the radiation. So they are spectral directional values, and depending on the material, you can have a different response in wavelength, of course, and also in angle. So what does it look like, this reflectance? Let's take the example of metals. So in metals, well, you have a distribution in wavelength. So you have a spectrum, a reflectance spectrum. So it's spectral reflectance. And of course, you have a different behavior and different response depending on wavelength. So for metals, you have, for instance, silver and copper here. So silver is this one with the plunge in the UV. You have copper and gold here, where you recognize because there is a drop in reflectance, which explains actually their color. Well, how do we perceive them anyway? Because what is reflected there is what we see, the color that we see. And you have aluminum, which is really interesting because it's highly reflective, even in the UV region. And as an example, as a reference, you have stainless steel here that is, well, less reflective than pure metals, but is still highly reflective. So why do I show you this? Because keeping in mind the applications, we can already see, looking at that we will have, the metals will be good infrared reflectors. They are actually used as laser mirrors. And they can also be good solar reflectors. Not all of them, but some of them. And there will be bad solar absorbers. So we keep that in mind for later. There is also another notion that is important in reflectance is depending on the surface and the roughness of the surface, you will have either or a mix of specular and diffuse reflectance. Specular reflectance, specular reflection, is when you have a low roughness compared to the incident wavelength. And with that, well, what's interesting is that you know the angle of incidence and you know the angle of reflection. You know where your in your radiation will be reflected, which is really important for mirrors for concentration. And if you have a roughness that is bigger than that, then you can have diffuse reflection, and then you know the reflected rays can go in different directions, and you don't know exactly where they're going, and well, it's not good for a mirror. So if we consider the applications, what is of interest for us is, in terms of performance, is to understand what are their solar weighted properties. And by that, we consider the incident radiation in terms of spectral, of the spectrum here with the solar spectrum. So our reference, because as I said, with concentration, you can only concentrate the direct spectrum, the direct irradiance of the sun. So our reference here is the direct plus circumsolar reference spectrum. So the solar incidence, if you consider here, you have a spectrum like this. And if you integrate it over wavelength, well, you have a value in watts per square meters, which gives you the value that you have in mind. So for global, it's 1,000, and for the direct, it's 900, approximately. Okay, so that is our reference. And now if we consider, for instance, a mirror. For the mirror, we wanted to reflect solar light. So what will be our performance criterion? It will be the solar reflectance. And solar reflectance is this value here, which is actually a ratio between the flux density in watts per square meters that is reflected by your mirror over the flux density that is received from the sun. So this one is the integration of the solar spectrum. So it's the yellow area here. And what is reflected by the component is just considering the response of your mirror at each wavelength of the solar spectrum. So at each value of the solar spectrum, you have a value of reflectance for your component, and you just multiply the two, and then you integrate all that over the whole solar range, and you have that value here. And if you want to visualize it, it's the green area here. So this is what is actually reflected by, in that case, it's a silver that is used as a reference. So you see that you have some optical losses here, and you have a global solar reflectance of 96%, which is really good. So what's to remember here is that this value has no unit, and it's no longer spectral. It's a total value integrated over wavelength. And it gives an image of the ability of the component to reflect solar radiation. So now if we look at the solar reflectance of metals, considering the spectral reflectances that we have seen before, so this is the integrated value, we find again here that great candidates for mirrors are silver and aluminum. These are the best metals to make mirrors because they provide the highest solar reflectance. The other ones, well, for instance, copper and gold, you've seen they are partly absorbing in the solar region, so they're not as good. Another thing to keep in mind is that, well, as you can imagine, we are not going to make mirrors, bulk mirrors with silver. That will be a lot of silver, and it's quite expensive. But the good news is you can make mirrors with only a thin layer of that metal using a support that usually glass, because it's much cheaper. And you can see here, if we go from the reflectance of glass here in black, if you add 10 nanometers of aluminum in that example on top of that glass, well, you reach already, you increase a lot the reflectance. And if you add up to 17 nanometers of aluminum, you reach the same reflectance as you would have with bulk aluminum. So with a small layer of metal, you can have the same optical properties as bulk metal. And that is why for concentrating mirrors, you have a glass support, which is a few millimeters thick. Why? Because, well, it's cheap, it's rigid, it's resistant to deformation, especially when you want to ship and handle, deliver it at a location for a plant, for instance. It's also easier to install because it doesn't deform. It's resistant to abrasion also, so it's good when you want to clean the mirrors. They're resistant, and you can have some abrasion from dust and sand. We'll talk a little bit about that in the third part. It's also resistant to corrosion, so it really provides a protection for the active layer, which is the reflective surface. And the reflective surface is a metallic coating that is deposited on the rear side of the glass. Well, it's deposited on top, and then you use it upside down. So the glass can protect the coatings. And you can see here that you have actually two layers of metals with different roles. I think I'll explain it just after that, just to say that behind the layers, the reflective layers, you have paint to protect the backside of the layer, of the reflective layer. And no, I'm switching there. So what is the role of these two? Well, the main reflector is the silver because it's the best reflector, as we have seen. And what is the role of the copper? Well, the copper has two main roles. The first role, well, actually, it's linked. The thing is, as you have, if you keep in mind the reflectance, spectral reflectance of silver, you have seen that there is a drop in reflectance in the UV. And this UV can be caught by copper. And why is that interesting? Because if the UV goes through the silver layer, it's caught by the copper and it can be reflected back up. And that is good also because this will protect the layers that are paints that are polymer usually, and that can be affected by the UV radiation. So you cut this radiation, you use it again, you reflect it again, and you protect the protective paints that are below. Okay. And we have other options for these solar reflective mirrors that are, well, less popular, but that exist and are at least at the R&D level, advanced R&D level. And you have this first option, which is known as the aluminum mirror. So the interest of this is that you can have a thin mirror, because you don't have this big plate of glass, because the protection is done by these layers here, by these coatings here. So you have coatings of a few microns here to protect the aluminum layer, because of course you have to protect it from oxidation, because aluminum, pure aluminum that is reflective, tends to oxidize at ambient in ambient atmosphere, so you have to protect it so it doesn't oxidize and remains pure and reflective. So you have these layers that are added, these oxide layers that are added to protect it from oxidation. But the whole thing is much thinner than the thick silver glass mirror that we have seen. So it can be also lightweight and flexible, easier to install, easier to transport. Well, there are a lot of advantages linked to that. The problem is they have, well, a lower reflectance than silver, and they have so far some durability issues. They are, well, less stable in time than silver for now. And there is a third option, which is a polymer mirror. And in that case, silver is back in the game. So it's the reflective layer. It's made of silver, but instead of having this thick glass support, well, you can have thin, flexible substrate, polymer substrates. So you have a thin mirror as well. So lightweight and thin. And it has a good reflectance because it's still silver. It's a bit less good in specularity. So what is of interest for us is the specular solar reflectance. And so the best remains the glass, the silver glass mirrors, but these ones are really competitive as well. But of course, yeah, there is question about their durability as well. So there is a lot of testing around that. And a few words about what we are looking at in my lab about this. So at the R&D level, actually it's simulations, optical simulations, that we don't fabricate them. But we have observed that it seems to be possible to reach performance that is equivalent to silver mirrors by using instead aluminum with a certain amount of layers of silicon oxide and titanium oxide. So we have some options with 8 layers, I believe, with optimized different thicknesses. And it seems that the performance could be equivalent to silver. And that is interesting because, as it was mentioned earlier today, there is a lot of tension on the silver resource because it's used in many other sectors, including PV. And so it would be a good idea to think about how to replace it. If we want to deploy concentrated solar, we need other solutions than silver. So that was the motivation for this work. There's a paper on that if you're interested. Okay. So now just a few words about how to make them. Well, it's mostly in the form of physical vapor deposition and mostly in the form of cathodic sputtering. So sputtering, in a few words, it means that you create, in a vacuum chamber, you create a plasma, which is an ionized gas from a neutral element like argon. It's really popular for that. And you have a target of a material that you want to deposit here, so pure material, for instance, silver or aluminum. And you apply a negative bias on this target, and the positive ions from the plasma phase will be attracted to this target and will sputter it and extract atoms that will be flowing in the vacuum chamber, and that will be forming a thin film on a substrate. Okay, so that's the basic notion for sputtering. Okay, so this is, well, what you find in most industries. It's this kind of technique. And I was talking about a metal, but it works also for oxides, nitrides, and a lot of other materials, of course, depending on the nature of the target and the nature of the gas. So for mirrors, the industrial production, I just show an example here, something that is popular, especially for aluminum, is to do a roll-to-roll deposition. So you have these big rolls of substrates here, and you send them in the deposition machine that is in the middle there, and you just unroll your roll and deposit in line on the substrate, and then you can put this on a structure. Then you can mount them on site, so you don't have to transport them. It's less heavy. So yeah, so it's the lightweight and easier for installation. Okay, I think that's the last one about the mirrors. Now, keeping in mind the three types of surfaces, we are going to consider the protective glass, which is not found in all technologies, but which is found in linear technologies. You have some window to protect the absorber, usually. So here it's in the form of tubes for the parabolic trough, where you have glass tubes surrounding the absorber. And here you have a glass window, glass panel here for Fresnel technologies. So, of course, you understand that we want that glass to transmit light as much as possible, because this glass has no optical purpose. It's mechanical protection and chemical protection. So yeah, we don't want it to interact with the solar radiation. So we want it to transmit as much as possible. So our performance criterion here will be the solar transmittance. And it's exactly built like the solar reflectance, except this time you consider the spectral transmittance of the material that you are considering. So at the bottom, you have the same reference. You have the flux density received from the sun, which is the integration of the solar spectrum in yellow. And at the top, you have, for each value of the incident wavelength, here you consider what can be transmitted by your material. And you integrate this behavior over wavelength, and you have a value in watt per square meters that gives you the flux density transmitted by the component. And the ratio, which again is a total value integrated over wavelength, illustrated the ability of the component to transmit solar radiation this time, is your solar transmittance there. And it is, sorry, and it is illustrated by this. So in dark red here, you have this value here, what is transmitted by the component. And you see that, again, you have some losses, of course. And so the full glass here, it's BK7 glass as a reference. This is its transmittance, spectral transmittance. And you can see that it gives rise to solar transmittance integrated over wavelength of 92%. So 92%, okay, it's good, but it can get better. of course, as you know, well, there are losses by reflection on glass. Now, some of you have glasses on their nose, and they know that. So you have a first reflection at the first interface between air and glass, and as it's transparent, it goes through, and there is a second reflection at the second interface of the glass with air. And so you have a combination here of reflections, and for each phase you have around 4% of losses that are reflected. And so overall, that's why you find a value of 92% of solar transmittance. So glass is transparent, but not entirely. So all the losses are reflection losses, and we want to reduce these losses. And for that, we have the entire reflective effect, which is based on creating destructive interference between the beams that are reflected on a coating that you will add between the glass and air. So it's a thin coating with a, I'll put it there, with a thickness that is in the order of magnitude of the light. So a few, or even smaller, so a few tens of nanometers. And so you have a reflection at the first interface, at the second interface, and what you want to do is create a destructive interference between these two beams. And to do that, well, you want them to be out of phase, and for them to be out of phase, you have a condition of the distance that they have to, well, go through, to cross. And if you can relate them to the wavelength here, you can have a destructive interference if you have a wavelength that is, a thickness that is in the range, well, that is a quarter of the wavelength, or a multiple of that. So that's why it's called a quarter wave plate. And so if you create this interference, you can cancel the reflection and cancel the losses. There is what we call the path condition, and there is a condition on also the refractive index of the materials. So here you consider the substrate, which is glass in our case, and 0 is, well, the ambient, so it's air. So we can be 1. And if you have the square, if the refractive index of your material, entire reflective material, is the square root of the refractive index of the substrate, then you can have a total extinction of the incident light at a given wavelength. So an illustration of this, it's hard to have an ideal situation, actually, but they try. The difficulty is to find an anti-reflective material that has a suitable refractive index to do that. So for glass, well, you have 1.52, for instance, around that. So you would need an ideal material with a very low refractive index of 1.23. And the material, the dense material with the lowest refractive index that we know is MgF2, and has a refractive index of 1.38. So what happens when you don't have the ideal refractive index? Well, you still have an extinction of the reflection, but not total. Well, we have a reduction of the reflection, but it's not a total extinction. With the ideal material, you can reach a reflectance of 0 at a given wavelength. But if you have a higher N, a higher refractive index, well, you will not reach 0. You will reduce it, but not to 0. There. And one thing that is a bit different from other applications, like glasses, for instance, is that here you want an entire reflective coating that covers the whole solar range, not just the visible part. And so in that case, the position of the minimum the ideal position of the minimum. If you optimize your coating, you will try to reach an extinction around 610 nanometers. That's the goal. If you if you reduce reflectance there, you will have the best effect to reduce the reflectance losses of the glass for the whole solar range. And of course, since the thickness is related not only to the wavelength, the target wavelength, but also to the refractive index of the material, well, you will have to readapt its thickness to have the best effect. Okay, that all is said. But there is a solution, thankfully, instead of using dense materials, you can use porous materials. So you can virtually reduce the refractive index by incorporating vacuum or air inside the material. So you can reach a value that is close to the ideal value that you are looking for to create this anti-reflective effect. And so this works with a number of oxides, and especially lower cost oxides like silicon oxide or aluminum oxide, while incorporating approximately half dense SiO2, let's say, will have the ideal refractive index for the anti-reflective effect. So this is how it looks like in effect. You have here the glass, and you have a porous silicon oxide. And the thing to remember is that you put that on both sides of the glass, because you have reflection or losses on both sides of the glass. So you put an anti-reflective layer on both sides of the glass. And if you do that with the correct optimized thickness, well, you reach the anti-reflective effect that is needed for solar applications. Well, if you are familiar with anti-reflective coatings, you would know that using several materials instead of one can be also a good option. And in fact, you can spread the anti-reflection effect on the larger wavelength range. But in the industry of solar thermal, apparently they prefer to have a simple option with a porous SiO2. And this is the illustration with actual collectors. So this is, the solar thermal panel that you recognize from earlier. And as you remember, there is a glazing, there is a glass panel on top. And adding this anti-reflective coating here, well, you increase the overall solar transmittance from 0.9102 to 0.97. So you really increase the performance of the glass. The difference between collectors without concentration and with concentration is just the nature of the glass that is used. For without concentration, you have low iron soda lime glass, because it's a cheap glass and it's sufficient for these applications. For collectors with concentration, they usually use borosilicate glass. It's more resistant to heating, for instance. It's more adapted, and so they also use porous silicon oxide on both sides of the glass, and to reach a higher solar transmittance. And they mostly do that using salt gel processes in that case. So some of you are familiar with this technique, and more than me, actually. But I just say a few words about it. So in this case, what you want to deposit is not a target; it's in the form of a soul that is created, and this soul is applied either by spin coating or dip coating, which means that in that case, you put a drop of the solution at the surface and spin it, and then it covers the whole surface. Here you dip your substrate inside the solution. You have your precursors. And then there is a heat treatment, a thermal treatment to stabilize and evaporate the solvents. And the interest compared to sputtering is that it's usually lower cost because there is no vacuum technology involved, and it's easily scalable. So you can have a large scale deposition, which is interesting, especially if you consider solar power plants where you have kilometers of solar field to cover. Okay, and that brings us to the last but not least type of surface, which is the thermal absorber. So the thermal absorber is the one where we want to absorb. So we want a high absorptance. So again, the criterion has the same form as before. You have a solar absorptance. That is the ratio between what can be absorbed by the material over what is incident from the sun. So incident from the sun, still the same spectrum here and the integration in yellow. And at the upper part, in this case, you consider what is absorbed at each wavelength. So it's 1 minus what is reflected minus what is transmitted. And why do we explain it like this? It's, well, simply because it's much easier to measure what doesn't go inside the material and what goes through the material than what happens inside the material. So if you want to know what is absorbed, well, you measure the reflectance and the transmittance, and you have the this information here for each wavelength. So if you integrate this, you obtain the curve in blue here. So this is the absorbed flux. So again, some losses. Sorry. A few losses here, and the reference here is the spectral absorptance of, in this example, it's a paint that you put on top of the thermal absorber. So it's a very efficient one. You have a solar absorptance of 96%. Okay. So this is the one I was talking about. It's called Pyromark. It's very popular for central towers because, well, it's very absorptive and it's easy to apply. But you have to replace it every few years. So there is a lot of maintenance that is associated with it. And there is also the question that it is highly emissive. And highly emissive means that you have thermal radiative losses that are linked to it. So a few words about that. If you consider your solar thermal collector as a whole, we consider the energy balance. What is incident is the solar radiation concentrated now in our case. What is useful is the energy that is transferred to the heat transfer fluid that is extracted from the receiver that can be used later on in the system. And the rest, well, they are losses. You have optical losses at the surface, usually by reflection. You have then your collector will heat up when it absorbs radiation. And so you will have losses, thermal losses. You have convection and conduction thermal losses, and you have, more importantly, radiative thermal losses. So if you consider what could be the efficiency of your solar collector, well, you can look at it here in yellow. So you have, well, the energy that is incident from the sun, I, which is a value in watts per square meters, in our case 900, for instance, which is the integration of the solar spectrum, the direct solar spectrum. It reaches the concentrator, which is our mirror, which has a surface, SC, and part of it is reflected. So we have our solar power that is here, PSOL, that reaches the receiver. The receiver has a surface S, has a solar absorptance that is alpha S, and has a thermal emittance that we will discuss just after that. And it is at a temperature that we will call T. So if we look again at the energy balance, well, for the receiver, it receives PSOL. It is extracted here, this power that is useful to the system. So we'll call it PU, that goes to the fluid. And there are losses that are thermal losses, and for the most part, there are radiative losses. So if we write the energy balance of the receiver, you have what is going inside, what is used by the receiver. It's PSOL, what is received, times what is actually absorbed by the receiver. So it's linked to its solar absorptance. And what goes out is PU and P loss, that we will consider here only losses by radiation, because we are going to work at temperatures where it will be larger than the other sources of thermal losses. We will get to that. So we have this expression. We have the expression for PSOL is linked to the solar irradiance, to the surface of the mirrors, and to the, we'll call it the efficiency of the mirrors. This takes into account the fact that they don't have 100% reflectance, of course, but it also takes into account the fact that there can be aiming errors that are inherent to the type of concentration. So you have some losses there. And the receiver efficiency in there is the ratio of the useful power over the solar power that is seen by the receiver. Okay, so you have these three expressions at the ready, and we are just going to say a few words about the radiative losses. So for the radiative losses, they are estimated considering the black body emission at a given temperature. And for that, we use the famous Planck's law that gives the spectral distribution of the irradiance of a body, of an ideal body that emits radiation, and this depends on its temperature. So the intensity and also the spectral range of this emission depends on the temperature of the body. So for instance, we are around here, maybe a bit hotter today. For the solar receivers in the range of 500 degrees, we are here, so it's ranging mostly in the infrared range. And if we increase the temperature, of course, we will reach the visible range. That is the case of the sun, which can be considered as a black body of around 5,800 kelvins. And like we did for the sun, our reference will be the total irradiance, considering the whole spectrum of the black body emission. And like we did with the solar spectrum, we just have to integrate over wavelength the spectral law, that is Planck's law, and we fall on the Stefan-Boltzmann law that is really well known, and that is depending on the fourth power of temperature, okay, with this constant, that is the Stefan-Boltzmann constant. So we have this, and this represents the irradiance of the body at a given temperature. So for instance, our absorber will be heated up at a temperature, and it will have losses that are related, that can be expressed with this equation here. Another thing to keep in mind before we give another definition is there is a law that's called Kirchhoff's law of radiation that states that you can relate what can be emitted by a material at a given wavelength and a given angle and a given temperature is equivalent to what is absorbed, or the other way around, actually. You can consider that if a material can absorb a radiation at a given wavelength direction and at a temperature, which is Tm in this example, well, it is able to maintain its temperature, to not heat up. It is able to re-emit this radiation at the same wavelength and in the same direction. So this is the Kirchhoff law of radiation, is this spot. So for our purposes, we can consider that if we calculate 1 minus what is reflected minus what is transmitted at a given temperature, well, we have access to the spectral emittance of a material, like we did with the spectral absorptance. And this is important for establishing our last criterion, that is the thermal emittance of the material. That is, again, a total value integrated over wavelength. You have a similar expression, except our reference here is no longer the solar spectrum, but it's the black body spectrum, okay? So here we have the black body spectrum. We have the integration of a wavelength of this black body spectrum, which is Stefan-Boltzmann law. And above, we have the spectral emittance of the material that is related to the spectral black body at the same temperature. So we can have an access to the flux density that is emitted by the component at the same temperature as a black body would. And if we consider here again our pyromag paint, so in that case I put spectral emittance, but it's the same that we had with the spectral absorptance, only we are looking at the infrared region this time. Then that is what is emitted by this paint at a temperature of 500 degrees. So you can see that you have a high thermal emittance of 75%. So it's a good absorber, this paint, a very good absorber, but you also have a lot of losses by radiation. So if we go back just to finish with the expression of the efficiency, which would be the solid to heat conversion efficiency or heliothermal efficiency, all of this we've already seen. We've just added the expression of the radiative losses here with Stefan-Boltzmann law. And if you combine these four expressions, you fall on this expression, which is actually an image of the flux that is absorbed by the material minus what is emitted, lost by the material, by radiation, over what is incident on the receiver. And it's the concentrated radiation in our case. And just here we make appear the solar concentration ratio that we have defined before, which is, as I recall, the ratio between the surface of the collectors, or the mirrors, over the surface of the absorber, to put it simply. So with all this, you have this expression, which is the heliothermal efficiency, which is related to the solar absorptance and the thermal emittance, the temperature of the material, and this is due to the mirrors, the optical efficiency of the mirrors, and the solar concentration ratio, and of course, well, the irradiance of the sun where you are. Okay, so now that we have this expression, we can ask ourselves, how can we increase this efficiency? So we'll look at the formula here. Well, you could think of increasing the solar concentration. So that's when you can use more concentrating mirrors, concentrating system like the solar tower, and more mirrors. You can adapt the number of mirrors for a solar tower. So you can increase the value of C. That will give less weight to the losses because there's a ratio there. You can also increase the incident solar flux. So that means, and that is what is usually done, you will go to regions where you have a lot of direct solar irradiance, including, like we said, the western part of the US, where you have, well, usually where you have deserts. So here you have deserts in the Andes, salt deserts. In Australia and North Africa and the Middle East, you have a lot of regions that are very good regions for that. And of course, you can try to increase the optical efficiency of the concentration system. So that means, of course, having better mirrors with the higher solar reflectance. But also, when you install a system of mirrors, you have to think about where they are going to aim. And you want to avoid, for instance, mirror shadowing that is shown here, where you have this heliostat that is reflecting part of the incident radiation on the back of the mirror that is before him. So that is one type of loss that you can avoid by thinking about how you are going to spread your solar fields. Okay, so that is what I would call acting on optics, macroscopic optics. And there is just a comment on this. This is where artificial intelligence and machine learning can really bring something. And there is a lot of R&D around that. How to, for instance, forecast the solar resource, so you can have better aiming strategies. You can provide advanced monitoring and control for the plants based on what we already know, what we have already acquired as data. You can do some predictive maintenance as well, to avoid stopping the plants, etc. And you can think about it in terms of, well, how to integrate it in the grid as well. So if you have some students that want to work on that, you can tell them about it. But going back to the materials, well, you can also think about acting on the materials, and that means increasing solar absorption and decreasing thermal losses, which means having a lower thermal emittance. This will also boost the heliothermal efficiency. And this is where we can act as well. So here is where I introduce the concept of solar spectral selectivity. So for a solar thermal absorber, the ideal behavior will be that of a selective absorber, spectrally selective absorber, meaning that it will have a different behavior, optical behavior, depending on the region of the spectrum. And this will give you the ability to have a high solar absorption, because in this range, this is where you want to absorb. So you will look at a low reflection, so you can increase the absorption. And in the infrared range, well, this is where you have the black body emission, which you want to avoid. So in that case, to avoid this, remember that you have the spectral emittance that is 1 minus what is reflected. So you want to have a high reflectance. So you don't have you have a low emission, and you don't have a lot of radial losses. Okay, so you have this opposite behavior depending on the wavelength range, and that is our selectivity for solar applications. This is what we want to reach. Oh. There. So why? Well, yeah. Remember what I had that here. So if we go back to the spectral reflectance of metal, we remember, well, let's look at the stainless steel, for instance, in here. We remember that, well, they are good reflectors mostly. And so they will not be very good absorbers, solar absorbers. But they are nonetheless used as support because, well, what we want is piping. We want metallic tubes where you have a heat transfer fluid and you have want something that is resistant to pressure and high temperature, high pressure. That is relatively cheap as well, and that is thermally conductive towards the heat transfer fluid that is inside. So that's why we will use metallic support. Depending on the application, we'll have a lot of steel or stainless steel, and sometimes higher temperature alloys. But this is the same types of materials that are used in other kinds of thermal plants, because we have the same problems at this level. But we also want an active, optically active surface, so we will add something on top of this metal to make it absorbent and selective if possible. So how to do that? Well, it's mostly in the form of solar selective absorber coatings or SACs. And the principle is this. You have a receiver that is a metallic receiver, and you will add a coating on top of it. That will be, well, mostly consisting in an absorptive layer. I say visible, it's mostly visible, but it's also near infrared and UV as much as possible. And this one is not one layer, usually. It's an association of layers or an association of materials. And what is mostly used is these two types, where you have either multi-layer between metal and dielectrics. So this one will create interference stacks, optically interference stacks, where you will, if you want, create a sort of anti-reflective effect for the receiver, trapping the light towards the receiver. Or you can have absorptive materials that are created as composites between a metal and a dielectric, or called ceramides. And to modulate the refractive index, you will have two different volume fractions of metal. So you will create a, here you have a substrate with a high refractive index. Around here you have, well, air, well, the ambient that is usually a low refractive, has a low refractive index like air. And so you would create a gradient of refractive indices here to trap the light again. So here you have a metal with a high refractive index as well. Here you have a composite with a lower refractive index, but with a high metal volume fraction, so still high. Then you reduce the volume fraction of metal, so you have the low metal volume fraction on top. And then you have a dielectric layer that is also low refractive index. So you have a gradient from high refractive index to low refractive index, and you can trap by, let's say, by refraction, gradually, you can trap the incident radiation inside. But that's not all. Then you can improve the efficiency of these coatings by adding an anti-reflective coating on top that is adapted to the absorptive layer. So you will further enhance the trapping. Sometimes in the composite here configuration, this layer, this top dielectric layer, is the anti-reflective layer. And at the bottom, you will add an infrared reflective layer, which is usually a metal, because as we've seen, they are very good infrared reflective. which is actually this layer here. And the role of this one is, well, mostly to, well, trap the infrared radiation that is coming from the receiver that is heating up. As it's heating up, you've seen that, well, it acts like a black body. It will emit radiation in the infrared range, and you want to trap this so it doesn't get out. So the whole system is not highly emissive. So these are the three main parts of a selective coating. So you can see that, yeah, we have structures with at least 3 layers, usually 4, 5, 6 layers, depending on the system. And so to create this effect, well, you have to go through a step of designing them. And how can you design them? Well, we have seen that the performance that we are looking for, solar reflectance, transmittance, well, in our case here, absorptance, solar absorptance, thermal emittance, and heliothermal efficiency, they are depending on the spectral behavior of the materials, reflectance, transmittance, and absorptance. But the thing is this, well, we can measure it, okay, by spectrophotometry, for instance. But we need, well, first we need specific equipment to do that. And then you need to have already synthesized materials. So you don't know what you're going to obtain. Well, you will not reach what you want to obtain if you go blind in what you are synthesizing. So what can be done is that you can predict these values of spectral reflectance, transmittance, and absorptance by calculating them from the optical indices of the materials that are constituting the whole stack. And you can do this before synthesizing, and it gives you a goal for the fabrication of the coating with the wanted performance. Okay, so this is what I will refer to as designing the coatings. And this is the mandatory step for that kind of material for the solar selective absorber coatings. You have to do that, otherwise you will not have something that is efficient. So in a few slides, these won't be the funniest ones, but just a few words about them. So like I said, you can determine the spectral reflectance, transmittance, and absorptance from these optical indices if you know them. And you can do that by considering the Fresnel coefficients that are describing what happens to light incident on the material, and that will give you the value of the amplitude of the reflected beam at the interface between two media, and you have the same with the transmitted beam. So what is to retain here is that this depends on the knowledge of the complex refractive index of the two materials, spectral values. So complex, I mean, it's the refractive index, small n, and its extinction coefficient or absorption index, if you want to call it that. So knowing this for the two media and knowing the angle of incidence on the interface, you can easily calculate, well, the angle of reflection there. So you don't need much knowledge to establish this. You just need to know the distribution and refractive index of the materials, the constituting materials, which you can find in databases. There are extensive databases on refractive indices, or you can measure them by ellipsometry, for instance, on separate materials that you want to stack later. So once you have these expressions, where if you have one interface, we have two media and one interface, it's easy. you only have one reflected beam and one transmitted beam. So you can use directly the values of the Fresnel coefficients at the interface. But of course, that's not what we want to do. What we want to do is predict what happens with the coding. So when we add a coding, we add interfaces. So the problem becomes a bit more complex because you have multiple reflections. Usually, your thin film will have a thickness that is in the same order of magnitude as the incident light in the case of solar light. So you will have multiple reflections. So you have first reflection when the incident radiation falls on the material. That's the one that doesn't go inside. Then a part goes inside and a part goes through and reaches a second interface where you have a second reflection there. So it goes back up. At this interface, part of it is reflected and part of it is transmitted back towards the air. So you have a second reflection that is coming out of the material. Then again, at this interface, part of it is transmitted. So this is one that's transmitted to inside the substrate. Well, in our case, it's the metal, so it will be lost there. It will be absorbed there. And part of it goes back up and again. So you have until, well, it disappears. So you have multiple reflected beams, multiple transmitted beams, and the expression to calculate the total reflected amplitude and transmitted amplitude becomes a bit more complex. Here you find the the Fresnel coefficients at the interfaces. So 0, 1 is between air and the thin film, and 1s is between the thin film and the substrate. So these two interfaces. So you have the Fresnel coefficients from before, and you combine them to understand what happens when all these reflected and transmitted beams combine. So here again, you have, well, an expression that is based on the knowledge of the refractive indices, complex refractive indices of the materials that are involved, and the wavelength of incidence. And you have a different behavior at each wavelength of incidence. So you have to calculate this for each wavelength of the incident radiation. So if you have the solar radiation, you have a lot of wavelengths. And again, well, usually we don't have only one coding, we have more codings. So you have more interfaces. And so here it's the other way around. So you have the substrate here and the ambient here. And you have something that is incident, some of it is reflected, some of it goes inside the last layer with a given thickness and a given refractive index. Then you have another interface, et cetera, until reaching the substrate. So you have all these values of the different thicknesses and the different refractive indices of all the materials that are involved in the calculation. And you have a total reflected amplitude and transmitted amplitude that is depending on these four coefficients here, M11, 12, 22, and 21. And what are those? They are extracted from what is called the transfer matrix. So the transfer matrix, it's just you multiply what happens at each interface. At each interface, something different happens depending on the angle of incidence of the light, because it changes as it goes through the different layers. So you have this big matrix where you have a 4-element matrix in the end, and these 4 elements are used in the calculation of the total reflected and transmitted amplitude. And again, all that you need to know here are the thicknesses and the refractive indices and the incident angle at the beginning. And all this must be calculated for each wavelength of an incident beam. So of course, you understand that this is not done manually. And when you have that, well, you just have to combine now to obtain the total reflected power, because here you still have complex values, because the value of the refractive index is complex. It's a complex refractive index. So you still have a complex number. If you want to know what is the total reflected power or energy, well, you just have to take the modulus of that complex number, and you will have as a result a combination of, well, these two values for two different polarizations. You have a reflection that is an average of these two. And for the transmission, it's the same, except here you have a bit more complex expression because you go through another material. For reflection, it's inside the same material or media, but for the transmission, it goes from one to the other. So you have to take into account the refractive index, again, in the calculation. And then you can combine them to find the spectral absorptions for each wavelength of an incident light. So you have this big calculation for a big stack of coatings. And for that, well, you have to calculate this and to predict what is of interest to you, which is the optical performance. You can use, well, commercial codes that are made for that. And, well, we use also in-house codes that can handle complex calculation and complex numbers and matrix calculation. Well, we use Solart and Python in our case because it's cheaper. Okay, just an illustration of what it looks like. So for these absorbers, if you consider here the stainless steel alone, as expected, you have a high reflection, so a low solar absorptance, 36% or something. If you add gradually the different layers that I was talking about, you have this effect. If you add just the infrared reflective layer, well, you will have a high reflectance here, and you will reduce the thermal emittance, which was 16, is around 2% now. But you still have a poor solar absorber. Now you add a composite here, a ceramic absorber. You will increase very much the solar absorptance while not increasing too much the thermal emittance. It's a trade-off, but it's still quite low. And if you add the last layer, then you will add an anti-reflective effect, and you will further reduce the losses and increase the solar absorptance whilst maintaining the low thermal emittance. So if you look here at the efficiency, we went from 26, 35, 81 to 88%. So all the layers have a role to play in here to find this final effect that we want, which is the selective absorber effect. Okay, so looking at applications, what happens in real life for collectors without concentration, you have selective coatings, which are based on ceramides as well. Here in this example is the titanium nitrides and oxynitrides actually that are mixed. And it's on the infrared reflective material is either copper or aluminum because they are good thermal conductors and they are quite cheap. So for without concentration, this is the type of infrared reflective layer that you will find. And you see the selective effect here with a high reflectance in the infrared range and a low reflectance in the solar range, and good high values of solar absorptance and low values of thermal emittance. So you have the selective effect. So even for collectors without concentration at low temperature, this effect is sought for to reduce radiative losses and increase the efficiency. And for the evacuated tubes, remember, it's something similar, except here it was a plate, metal plate as support. Here you have coatings that are deposited on glass. but it's the same structure. You have an infrared reflective layer, usually copper. Then you add a visible absorber here. In this example, they have chosen, well, in these two examples, actually, two technologies, they have chosen composites between stainless steel and aluminum nitride or carbon. Why stainless steel? Well, because it was available in their line of production. So by sputtering mostly. And often you will find that the anti-reflective is a dielectric that is also the one that is used as the absorber. So again, to simplify the fabrication, you have the same materials to deposit. So yeah, again, high solar absorptances and rather low thermal emittances, so a selective effect as well. And here's just an image where you can see the different types of layers, but of course, in the end, you only have this over the whole tube with all the layers. Now, considering the collectors with concentration, for the example here of the linear receiver for parabolic trough technologies, remember that you have a metal here where you deposit an absorber coating. By the way, you have a glass here where you deposit an anti-reflective coating as well. And the whole is working in vacuum. So in that case, they are using this double composite, double cermet structure that I was talking about. And it's based on molybdenum and silicon oxide for this example. You can also have tungsten and as metal, and you can also have aluminum oxide as the dielectric. Why? Because these materials that are stable at high temperature, that's why they are chosen. And you have, again, the selective effect. And here you have a low thermal emittance at high temperature than we had in the other examples. So you can see that the transition between the absorption and the reflection here, or low emission, has moved a little bit to account for the fact that the black body is not at the same position. When you increase temperature, it gets closer to the solar absorption. So the selective effect is more limited. Just an example of how it's deposited is, again, sputtering. These are lines of production of absorber tubes. Nothing much to see there. Just a word to say that there is some R&D on these coatings. There are commercial solutions, but mostly they work in vacuum, like I said, or you have the paints, but they are not selective. And so there is R&D to produce coatings that are stable at high temperatures and that can work in air at these high temperatures. And an example of what is developed is this type of material, which is the titanium aluminum oxynitrides, let's say, or a mixture of these that are used usually in the tandem form, where you have two materials with different refractive indices, like we said before, to adapt to the incident radiation and create a gradient in refractive index. And you have an anti-reflective coating on top also that is, well, a standard anti-reflective material. And just a word on what we do in our lab about that. We also do a lot of research on these absorbers, so selective absorber coatings. We create multi-layer architectures. In our case, it's not tandem, it's more on the interference stack part, where you have metal and dielectrics that are stacked together will extinguish the incident light. We deposit them by plasma deposition techniques, sputtering, but also plasma-enhanced chemical vapor deposition, where, well, what happens in the gas phase. Well, it's more of a chemical effect than just a purely physical effect, as I've said before. And the development strategy for these types of materials is there's always a step of optical simulation, optimization, and design that is based on the knowledge of the behavior of the layers taken separately. So they are developed separately first, and then there is a design of the stack. Then the stack is deposited by, well, in our case, by plasma processes. And then you have to characterize the materials to check that you have obtained what you were looking for. And if not, well, you have to work again on the design part to adapt it. And there is also the part about the aging. You have to check the aging of the materials to see that they are stable in time. So I don't have a lot of time left. I will just maybe choose 1 or 2 slides to discuss this durability part. So you remember that, well, we have different harsh conditions of use, especially for concentrated solar, or often in deserts. You can have also deserts on the seaside, like in the Middle East. So for mirrors, you can have a lot of erosion due to sand and dust, especially if you have storms, and this can impact the specularity of the mirror. And so they become more diffuse and they are less efficient. So they, like this, you have a loss in reflectance by several %. And of course, it depends on the type of sand that you can have. So there are tests that are indoor tests that you can do to check that. And there's also the problem of corrosion, edge corrosion, and peat corrosion for these coatings. So sometimes there are solutions to protect them in greenhouses, so you don't have that problem. And also, well, you have less erosion, less soiling, and you don't have to clean the mirrors as much. So you don't have to consume as much water to clean them. Well, these are just common strategies to check the durability, just to say that you have standards to check them in damp heat, in also considering salt sprays for seasides, thermal cycling, checking the effect of UV and humidity. Well, there are a lot of standards for these, and also for paint coatings, for absorber coatings, which is for paints that can be used. And for absorbers, it's even worse because, well, they have to last, of course, long, but they will work at mid to high temperatures. They will, for some of them, work in ambient air. So you have oxidant atmosphere, corrosive atmospheres. You can have heat transfer fluid that are corrosive as well, like steam or molten salts. You have high thermomechanical stress with thermal cycles of high amplitude between day and night. If you have the sun coming, if you have a cloud in front of the sun, well, the irradiance drops a lot and then goes back up. And so you have a lot of thermal cycles due to that. You also have pressure inside the receiver. So mechanical stress for the receiver, temperature gradients that are different. You can also have corrosion, like I said before, because you have a lot of fluids that are corrosive in these applications for the absorbers. So there are preventive measures. Well, you can select materials that are stable in oxidation at high temperature. This is the case, well, we can use nickel-based alloys. In the case of central receiver, because, well, you only have one receiver, because it's quite expensive, but you only have one receiver. So it's acceptable, and it's really, well, much more stable than other types of alloys. What can I say? And then you can have the problem of the diffusion, atomic diffusion inside the absorber coatings. So this is an example. Well, you have the diffusion of oxygen from ambient inside the coating. And you can also have a diffusion of the materials, like, for instance, here, aluminum, that goes back up here So the problem is that you will change the optical nature. By changing the chemical nature, you will change the optical nature of the material. And that can be, well, detrimental to the optical properties. So here we have a decrease in thermal emittance, an increase in thermal emittance and a decrease in solar absorptance. Okay, and you can also tune the fabrication process to have something that is more dense, for instance, to block the diffusion, depending on well, for instance, the pressure and the temperature that you used for sputtering in that example, to avoid the diffusion. But the problem is that if you do that, you can change the optical behavior and the optical nature of the material. So, well, you have to choose wisely between the two. And I think it's one of the last ones. Yeah, that's just a few words. There are accelerated aging strategies that can be applied, like the Arrhenius method, where you determine an activation energy for your degradation, the degradation of the optical property, in that case, solar absorptance. And once you have that, you can do some lifetime prediction, considering a yearly rate, and then with the number of years that you want to operate at a given temperature, you can predict how much time it will take to reduce the performance by a given amount. So, for instance, here after 25 years, they say that they only have reduced the absorbance by 1.5%. And in our case, we are also studying the effect of concentrated solar irradiance using our solar furnaces, because, well, it's a different irradiance, not just thermal, it's also, let's say, an optical electromagnetic radiation that is falling on the materials. So using just an electrical furnace, you will not have this information, this additional information. So we are also studying what happens when we heat up under concentrated solar irradiance. And that's just, well, the end, the takeaway. I hope I've convinced you that solar thermal is a valuable option for the future, especially when you want to produce heat directly. So there are a lot of applications, and especially industrial purposes, industrial processes here that we could help. I wouldn't say that it's easy to do, but the concept is that you choose the support material and you have a surface functionalization for optical performance. So that is something that is known in the field of optical coatings. And, well, the development strategy is the one that I said before. You need to think about, well, the step of designing the material. It's really the most important part that you have to consider here to really target your optical performance, is, yeah, to predict it and optimize it before you create your materials. And there I just recall the requirements for the different materials that we have already discussed. And so with that, I thank you for your attention. I thank all the people that I haven't named here. Sorry about that, but I didn't have enough space to thank all the people that were involved in all this work. And if you have any questions, let me know. Thank you.